Hi, my name is Jennifer Yee, and I'm here to talk to you about my paper on a microlensing event. This event is called MOA 2010 Bulge 311, and it was very exciting because it was a high magnification microlensing event. In this case, the source was magnified about 600 times, and this made the event very sensitive to planets. This is the light curve of MOA 311. The event brightened by more than 4 magnitudes. If I zoom in on the peak of the event, you can see that it has a rounded shape due to finite source effects. This event peaked over New Zealand, and the peak of the event was covered by MOA, the B&C Telescope, Vintage Lane Observatory, and Mount Canopus. The falling side of the light curve was observed by SAAO and Bromberg Observatory. When we fit a point lens model to the data, we get a pretty good fit. But it turns out that if we include a planet around the lens star, we get an even better fit by delta chi-squared of 140. Here are the residuals to the point lens and planet models. The dashed lines show the limb crossing times, which is when we expect to see small signals from planets. The two plots look very similar, and there isn't an obvious signal from the planet that accounts for the delta chi-squared. Another way to understand the planet signal is to look at the cumulative chi-squared. Each data point should contribute delta chi-squared of 1, so it should be a straight line with a slope of 1. We can then subtract off this line and plot something I call the chi-squared residuals, which should be a flat line at 0. If there's a small signal in the data that isn't being fit by the model, this will cause a break in the cumulative chi-squared and a discontinuity in the chi-squared residuals. If there are systematics in the data, the chi-squared residuals will have a slope, but the signal is still apparent. Here are the chi-squared residuals to the point lens model. You can see they have a slope due to systematics, but there is also a jump around the time of the first limb crossing when we expect to see planetary signals. If you compare this plot to the chi-squared residuals to the planet model, you can see that the jump disappears, indicating that the planet model fits the data better in this region. If we take the difference of these two plots, which takes out the systematics, the signal from the planet is even more clear. So what we have here is a planet model that fits the data better than the point lens model. And a large fraction of this planet signal is coming from the limb crossing time, which is when we expect to see a signal due to a planet. But we aren't claiming a planet detection, and the reason is that we're worried that this could be due to systematics. So we're classifying this as a planet candidate. The smallest signal that's been published for a planet in a high magnification event is delta chi-squared of 880, which is seen in MOA 2008 Bulge 310. In this case, there is a clear signature of the planet in the residuals. These two events may also be compared to MOA 2011 Bulge 293. In this event, if you take away the follow-up data, the planet signal is only about delta chi-squared of 500, and it is right on the boundary of detection. Defining the detection threshold for planets is becoming more important for microlensing, as we're moving away from publishing individual planets to systematic analyses of the data. Taken together, these three events give a sense of where the detection threshold should be for high magnification events. We have a firm detection at delta chi-squared of 880, a possible detection at delta chi-squared of 500, and something too small to claim with confidence at delta chi-squared of 140. This is the first empirical study of the detection threshold in high magnification events. Interestingly, it also seems that the detection threshold for planets in high magnification events is different than for planetary caustic events. In Ogle 2005 Bulge 390, the planet was detected at delta chi-squared of 550. And it seems likely that these error bars could be inflated quite a bit without diminishing our confidence in the signal. We think that the reason for the different detection thresholds is that in planetary caustic events like this one, the planet signal is separated from the peak of the event, so the planet parameters and the microlensing parameters may be determined independently. This is good for microlensing surveys, since most of the planets they will discover will be in planetary caustic events rather than in high magnification events. Thanks for listening to my coffee brief on MOA 2010 Bulge 311. If you have any questions, you can contact me at jyee@astronomy.ohio-state.edu.